right. So I'm going to talk about collaborative autonomy and the role of AI broadly, and I'm going to talk about a specific instance of how it is used to design controls in one of my previous projects. So I assume everyone here has heard of AI. Probably some have heard of collaborative systems and some on autonomy, but I'll talk a little bit more about all of these things and what I mean when I say AI for collaborative autonomy. All right. So before I get there, I want to briefly talk about some of the areas of research that I work on and my students work on and my collaborators do. So we have three uh, thrust areas. The first is dynamical systems and control. So dynamical systems are systems that evolve over time, and how to understand these systems, how to regulate these systems, what are the types of ways in which we can uh, ensure that these systems are secure, robust, efficient. These are problems that are studied in under dynamical systems and control. AI is very broad. My focus within AI is mainly on developing computational methods, algorithms that make systems efficient, and particularly I use a lot of artificial neural networks and reinforcement learning in my research projects. And the third uh, thrust is on computational neuroscience. So it is one of those grounded domain-specific area where there are specific problems that come from neuroscience, psychology, cognitive science, and they pose a lot of challenges to the AI and other tools that we develop because they expect us to answer certain questions for which some of these tools are not naturally tailored for. Right? So that's where our group is interested in working on research problems. So there are some of these target applications that would help you ground whatever I'm talking about into some practical uh, applications that you are much more familiar with. So the first application theme you can think of uh, cyber physical systems. So examples of them include smart grids, wireless sensor networks, water distribution networks, transportation networks, and so on. So here, if you think of these systems, one of the things that you want to study or when you think is more useful is how to make them more efficient, right? So how to make their performance much more conducive to what is demanded out of these systems. And those are the essential questions that control researcher addresses targeting its application. A second theme, you can think of systems which are not necessarily engineered by humans, but systems that are naturally occurring, right? So some examples include neural networks, drug delivery systems, and social networks that naturally evolve, and epidemic networks. So for these types of systems, the problems that one would be interested in is how to actually model these systems, how to actually gain insights about how these systems evolve over time, what are the mechanics that influence some of the features that uh, are present in these systems. So these are the fundamental questions that we would like to explore. And the third and final theme I would like to highlight is there are certain systems which are often referred to as population systems. So these include swarms, robotic swarms, quantum systems, cellular populations, open and neural ensembles. These are systems that naturally occur as populations, and these are systems that are very difficult to handle with uh, classical tools that are available, and therefore anything that we can do about these systems, for example, how to effectively model these systems, how to understand or analyze properties of these systems, and how to design strategies to regulate such systems. Any of these things, if we can come up with better ways than what we have now, they will all lead to some meaningful impact in these domains. Right. So, if you think of all these different themes that I pointed out, there are two things that are common across all of them. So, these are all systems that have some dynamics. And when I refer a system as dynamical system, all I want to say is that these are systems that naturally evolve with time, right? So there is a property of the system that changes over time. And most of these systems are interconnected in nature. They are connected with units that are similar to themselves or different from themselves. And most of them, they generate a lot of data, right? So then the main reason why AI or machine learning or anything that is related to what we are interested in is that they generate a lot of data, how we can make sense of this data so that there is some meaningful action that can be taken from this, right? So that is what we are interested in. And the overall uh, uh, summary that I would highlight is we want to build systems that can monitor themselves, communicate with each other, and self-govern. And that leads us to what is known as autonomy, right? So I want to build autonomous systems, and these should be capable of self-monitoring and self-governing in a productive way. Right? That's the whole idea. All right. So now I'm going to talk about collaborative autonomy and some of the problems that are important in this domain and why AI is considered as a potential way to address some of these problems. And I'll give you an example if we have time. Right. Okay. So, what is collaborative autonomy? So, if you have systems and multiple such systems can exist and work together to accomplish a common goal, and that is more useful than just one system operating or working to achieve a given goal. And sometimes we want these systems to collaborate while retaining their autonomy. So we want to endow each of these systems with their own ability to perceive their environment, take decisions, while also collaborating with other systems so that they can achieve a task that neither of them can achieve independently or working by themselves, right? So there are three components. There are at least two or more agents, and each of these agents have their own agency. So when I say agency, all I mean is they are capable of perceiving their environment, they are endowed with a decision making capability, and they have to work together to achieve some common objective, right? Now, if you again think about this setup, you can consider or you can come up with a lot of challenges or design problems that you have to tackle. First, if there are more than two agents, what is the role that you have to assign for each of these agents? So, for example, if I have multiple bots that are working in a warehouse, they are trying to pick up objects that are fallen down, move them to a particular place, stack them back. And there are multiple robots, each of them have similar capabilities. So, which robot will take which task, right? So, it is a problem of role or task assignment. Second problem is communication. So if there are multiple agents, you have to establish a way through which they communicate with each other so that they don't do conflicting things. Right? And third is information sharing. So, for example, if one robot is able to sense that there is a blocked path, how does it communicate with the other robots so that none of the other robots spend time coming to this place and figuring out for themselves, right? So there should be a way to establish a common world model or common model for the environment where they operate in so that they know what each of them are talking about when they share information, right? And then there is something known as local versus global decisions. So because we want each of these agents to be independent while also collaborate with others, then there is a potential that I have a local decision making capability, but I also have to collaborate with others. So I have to establish some way of decision making that leverages both local and global decision making capability, right? And that is especially important because when there are conflicts, so for example, it is good for me to just, as a robot, if a robot has to take a decision, it probably is good for the robot to just stay in its place so that it doesn't expend energy, so it saves battery. But it would be better for the team if the robot pushes an object or lifts some object for a few seconds, right? So if there is a local objective, there is a benefit locally, but there is also a global requirement, and there is a a conflict between these two, then there should be a mechanism to resolve these conflicts, right? And then a lot of the other things are mostly technical, which is if there is a task, it has to be done robustly, meaning there should be there are a lot of uncertainties in the environment where some of these robots may operate in, and it should be able to uh, perform those tasks despite of some of these uncertainties. Then there is something known as trust, which is excuse me, very interesting in some of these collaboratively autonomous systems that are not necessarily robotic systems. So we'll talk about one example, and then you have to have adaptability, meaning if there are multiple robots and they are working as a team, if one of the robots is down because of energy or batteries drained, then some other robot should be able to adapt its role so that it covers for the missing agents and so on, right? So that is adaptability, and all of them should be operating safely so that they protect their own physical structures as well as doesn't harm others. Then we should be able to scale, right? So one of the things that is very important in these types of systems is that if I add or remove an agent, it shouldn't affect all the other components that are already pre-designed, right? Otherwise, it's a very painstaking task to make this team flexible. Now, in all the examples I gave, I only talked about robotic systems, but again, it is just an example. It's not necessarily the only way you have to think about this. And hopefully, one of the examples I give in the next couple of slides will clarify that or make this point clear. Now, I said that for collaborative autonomy, we are going to bring in AI, and I want to make sure that this is clear that AI is not an elixir for every problem, right? So you have to have a reason why you need an AI model or a tool to address a specific problem, right? So most of the problems that I mentioned are suffering from what is known as ill-posedness. So it is a very specific mathematical term that defines the solvability of the problem. So most of the time you operate in situations where your problem itself is mathematically ill-posed. So you don't have a way to find solutions directly using without using learning tools, right? So because of that, we need some form of assistance from learning models, and that's where AI comes in.
Quick question.
Sure.
So are you doing that via like a model view controller to the robotic agents, or how are you addressing that today?
For the robotic agents, the example that I'm going to talk about, it's not based on model, it's based on data-driven control using neural networks. Does that answer your question?
Well, are you like, do you have your own sort of Chat GPT version that you're using, or like, are you using Azure Cloud, or do you have your own tools?
No. So yeah, so technically speaking, ChatGPT is a neural network. So in our work, we use neural network, but we don't have to design neural networks uh, of the scale of a ChatGPT, right? Uh, you will see that some of these problems involving robotic systems, at least, they don't require a very complicated neural network model. Simple neural network models that run on chip on the robot would be enough to solve some of these problems.
No, I wasn't saying like the robot itself, but like when you're doing collective autonomy,
Yes,
like
right. So there are two versions. So in and it depends on the application. So for the application involving robotic systems, it is still not using cloud or any of these big models. We can make do with whatever compute that is available in individual bots, right? But there are other applications where you require powerful compute and capability that demands cloud or other services, and I will mention about them. Right? Okay.
Excuse me.
Yes.
Uh, what did you exactly mean by learning tools in this scenario?
Learning tools.
Yeah.
So when I say learning tools, I mean specifically for our work, we all use in all our papers we use neural networks as the learning tool, but it could be general. Any uh, model that you can train and learn something from data. It could be a learning tool, right? Does that answer your question? All right. All right. Okay. So in the next few slides, I'm going to just mention some of these problems in a very concrete application domain. So the first is designing a collaboratively autonomous team. Uh, uh, Problem involving end-to-end design. So you design the behavior of each agent and also how they collaborate with each other, right? The second problem involves application domains where you design just the collaborative behavior and only a set of agents, right? Not all the agents. And this can be further subdivided into two categories. So you design only a subset of agents where the other agents are uh, not trying to actively stop you from doing what you want, right? That is a cooperative setting. And the last case is you are still designing the collaborative mechanism and a subset of agents, but the other agents that you are not designing uh, are trying to compete for the resources that are available or something else, or their objective itself is diverse or different from what you want to achieve. All right. So is the first example. So this is a very concrete example where we have to design multiple heterogeneous agents. So if you have, for example, a reconnaissance mission, or you want to track something, and especially if it requires you to track something in hazardous environment, so you typically want to involve, let's say, ground robots or surface robots on water, as well as drones that are air vehicles, right? So you have heterogeneous agents, you have ground robots or drones, and you want to design uh, ways to control all these heterogeneous agents, and also have to design how they cooperate or collaborate with each other, and how they share their information among each other. And for this, there is these four things that we are focusing on. First is what happens when there is loss in communication from one agent or to one agent, right? How do we address that? How do we ensure that the information shared is private, so that it is not open for uh, other agents that are not necessarily uh, supporting what these agents are doing? And then the last component is, if there are agents that are uh, running into a downtime due to some issue, how do we detect these agents and isolate these agents so that they don't harm the overall uh, task that we are getting into, right? So this is a concrete example for the first case, where we define individual robots, how they are going to behave, and also how they cooperate with each other, right? So this is the first example. And this is a second example. Here you have the same setup, everything is same. So you have all these different robots, ground robots, surface robots, or drones. But now you also have human operators, right? Now, if there are human operators, you cannot design human operators. If there are multiple human operators operating a drone, each of them, they have their own way to interpret and apply. One way for you to easily think about this is, if most of you, I think, drive car, or at least are familiar with the current generation of cars, which come with lane tracking assist, or you have adaptive cruise control in most of them for a long time now. And some of these, particularly the lane tracking assistance system in most cars, if I'm not wrong, if you don't touch the steering wheel for more than 15 seconds or some threshold, it will prompt you to hold the steering wheel, right? So you can think about what is going on. So you have a lane keeping assistant, which is autonomous autonomy enabling software in the car that keeps track of your car. It perceives the environment, it perceives the lanes, it keeps track of the lane, it ensures that your steering angle is perfect so that your car navigates within those lanes. But it requires every few seconds a human operator to hold the steering wheel for safety reasons, right? Now, if assuming that there is no such safety constraint, right? Either your lane keeping assistant will autonomously enable autonomous lane keeping, right? Or you may have humans who are totally in control of the car steering, so that they fully control the steering of the car, right? Now there is these two extremes, right? So there is an one extreme where everything is fully autonomous, or another extreme where humans are fully in control, right? But there is this problem in some of these application domains where you need to seamlessly transition between who controls or who is in control, right? So, for example, if there is a drone that is operating and if the environment is foggy, you don't want the pilot sitting who is looking at the camera feed to operate the drone, because whatever the uh, drone operator sees is just a foggy image, nothing is visible, right? But at these time instances, it is useful for an autonomous software that uses LiDAR data or data that is not corrupted by poor vision to take control and actuate these drones, right? So how do we enable this transition from the software that we design versus a human operator who is actually physically uh, working, right? So this transitioning mechanism is the collaborative mechanism that I talked about, because if you think about it, a fully autonomous drone is autonomous. Human operator is also capable of perceiving the environment and taking the decision, right? So both are autonomous agents, and how they can collaborate with each other is the uh, problem that is being addressed in this particular project, which I'm showing here as an example, right? I think. Sorry, I think that's. All right. Okay. So this is the third example, which is moving away from robotic systems. So here is an example where you have all of you are familiar with chatbots. You might have used chatbots at some point when you visit a website or when you are trying to figure something out, or most popularly when you are really in need of some customer service and all you get is a chatbot to talk to, right? So imagine you are you want to develop chatbots for some application. Here I'm mentioning about health application, but imagine you want to design chatbots that is useful for a specific application, right? So these chatbots would be useful if they are as good as a human who is providing answers to the questions that a customer asks, right? So they cannot be pre-coded bots which retrieve specific answers based on a given template to all the questions you ask. First, that. Second, you want them to be very safe. So you don't want these bots to act in a way that is unsafe to the customer, right? And provide information that potentially puts the customer in an unsafe scenario. Third, this brings us to this specific uh, point where if there are chatbots that are capable of acting close to how a human would react to a specific question, then they should have some degree of autonomy, right? So they should be able to perceive, which is to take in all the input that is given to the chatbot. They should have a decision making capability where they process this input in some way and then retrieve and give an answer for that particular input, right? So these chatbots should be autonomous. Now, there are multiple such chatbots that can be deployed, or you can have multiple human users talking to a chatbot, right? Now, where does this collaborative autonomy comes? It comes in this particular subtle way, right? So if the chatbot has to be successful, it should work with the human who is interacting with the chatbot, right? It should try to understand what the human wants. The human should be the human is autonomous, so they will act in a way that is maximizing their utility. For example, if I talk to a chatbot, I want to get a specific information, so all the prompts that I provide will be targeted towards getting that specific information that I want, right? So if this interaction has to be successful, the chatbot has to collaborate with me so that it asks questions for clarification so that it tries to also give the specific information that the human is seeking, right? Does that make sense? So that is why this a very interesting application where collaborative autonomy uh, comes into picture. All the problems that we talked about in the context of robotics also apply in this setup, right? You have to design these chatbots which are fully autonomous. They should be able to come up with solutions to questions that are provided to them. Second, there should be a conflict resolution mechanism, meaning if the chatbot is trying to provide some answers based on the information it has received, but it is not satisfying the humans, the chatbot should find a way to break this deadlock, right? And three, it should be robust, it should be safe because multiple humans can ask for the same information in different ways, right? So one person can ask the same question in a way that is very different from another person, right? So despite these uncertainties, the chatbot should be able to provide information in a meaningful way. All right, so this corresponds to the second case where you can, in principle, design a subset of these agents, which is the chatbot, and the collaborative mechanism, how the chatbot tries to collaborate with the humans who are seeking information from the chatbot, right? So that is the second approach. And this is uh, the last example. And this is an interesting example because here you have uh, a bunch of uh, agents. Let's assume there are a bunch of users who are using social media platforms. And there is, for example, an official weather agency reporter or weather agency has an official handle, let's say, and they are putting out information about the hurricane Erin or something else, right? So you have this information that is being shared, and that information is being spread across this network, right? Let's assume there is another agent who doesn't want the correct information to go to all the uh, users of this social media platform, right? And they are trying to actively uh, uh, flood this network with information that is irrelevant. Okay. Now, this is a situation where you have a system where multiple agents are involved, each of them are autonomous, and you want to ensure that right information reaches all the people who need those information, right? Now, here, if you think about it, you want to define uh, policies for agents who are interested in sharing the right information when, for example, there is no other information is being shared, right? So this could be in the context of marketing, right? If you are going to sell, for example, ChatGPT to all the universities, you want to put out the right information to all the users, which is the university management who are responsible for buying the license for using ChatGPT, right? Now, this is a strategy for information dissemination when there are no competitors. Now, let's assume there are multiple competitors, right? So, like ChatGPT, there is Facebook Meta, which is coming up with their own large language model. Every other company now comes with a large language model, and they all want to sell this their model to universities, right? Now you have multiple agents, they all have competing objectives. And how do you operate in such a situation? How do you design policies for individual agents so that they maximize their utility or they achieve their objective? So that is this application where all the problems that I talked about still applies, where the problems are still ill-posed. So if I have to give an example, so if you are going to design your marketing strategy for spreading information about the utility of your product to all the users, while doing that, you don't have information about what other information that are seen by these universities or your consumers, right? So you're operating in an environment where the information you have is partial. Does that make sense? So if you know, for example, all your competitors, all their offers to the universities, you can come up with a policy that ensures that you are successful. But when you are designing your policy, you don't have information about all the other competitors' offers to these their consumers. Does that make sense? So you are operating in an environment where you have partial observability, and you have to design a decision-making model that ensures your objective is successful, right? So this is a classic case where the problem itself is ill-posed, so that you need some way to learn solutions using examples which are collected over a period of time. All right. Hopefully this is clear. All right. Okay. I have 10 minutes, so I'll run you through a couple of examples that are very specific. So this example is an example related to cyber physical systems. So cyber physical systems, the application you can think of is just a robotic application. You have a communication component, you have a physical control component, and you have a system, and you have to take decisions, right? So typically, all decision-making problems can be represented using a block diagram like this. You have a plant, which is often referring to a physical system. In this case, it's the robot, let's say, and it is equipped with a sensor, and that sensor monitors what the system is doing, and that data is shared to a controller, which is either a cloud or it's within this a controller that is mounted on the plant itself. It can be either, and the controller decides how to actuate the system so that the plant uh, acts in an appropriate or a desired manner, right? So this is a classic control block, and it is useful to think of any decision-making problem by superimposing these different components in such block diagrams so that you can understand what's going on. All right, so one of the things that is interesting or useful in this project that we have done is you have these systems that you are monitoring, but how frequently you should communicate what the system is doing to the controller. So if you are monitoring, for example, a substation or a traffic network, do you have to continuously monitor or continuously turn on your camera 24 hours to see what's going on at a traffic intersection, or do you need fewer time instance when they should be turned on, right? So that's what is being addressed in this particular block. So you have a mechanism to monitor and decide when you share the information back to the controller. Right? Now, one of the common problems with any of these types of systems is this system behavior is usually not fully known. You don't fully know how the system would behave accurately. Right? Now, typical or at least 10 years back, how these controllers were designed is mostly based on what is known as time trigger mechanism. So the idea is you have a predefined sampling time, and you repeatedly take measurements at this sampling time so that you share that information that frequently. And this is based on what is known as Shannon. Are you familiar with Shannon? Claude Shannon. So he, if I'm not wrong, is a Nobel laureate. He is father of communication sciences. So he defined this condition for uh, defining or measuring or sharing information in a lossless way, right? So if you sample at the predefined sampling time, you will be highly conservative because you take more samples than needed, but it was provably efficient in restoring all the information that was transmitted without loss, right? So that's why this criteria was followed for a long time. Then in 2000s, someone came up with this idea of event triggering. I say someone because uh, the term was coined specifically by researchers in UCSD, San Diego. But the idea of doing this type of sampling has been proposed on and off by a lot of researchers over a period of time, even since 60s. All right. So with that, what we can do is, or what we have done is, we have come up with this type of system where you have a plant or a system that is being monitored, and we have shown that if we can collect data at specified instances, not necessarily as frequently as was required before, we can come up with learning rules that ensure that your system is uh, operating or meeting the desired objectives for which you sought to design these types of controllers. Right now, so mathematically, there are a few things that are very important. Some systems are linear in how they operate. Some systems are not. So we have done this for all types of systems, including linear, nonlinear, network systems. And I'll skip this slide, but I'll talk about this example. This is what I wanted to uh, highlight. So I gave you one of the application areas where we deal with population systems, right? So you have multiple agents that are uh, organized in some way, and they are either operating together, or you, for example, this brain or neural system, there are different levels in which people study these systems. So you can study neural systems at a cellular or molecular level. You can study these systems at individual neuron level. You can study neural circuits, or there are researchers who study brain regions or the whole brain at a very coarse scale, right? And there are different ways these at individual scales people study and use that information to come up with solutions for certain problems. Now this field, you can often refer, or you often see that these types of system are referred to as ensemble systems. So the way you can think about it is, if you have a population, each system is represented by a physical law. In this case, because it's a robotic system, they adhere to laws of physics, and each system has their own laws of physics, right? And they can be represented compactly in some mathematical way. And the goal of controllers or control design for these systems is, you want to come up with actuation signal, or how to operate the motors in these robots, so that you can control this collective behavior of these robotic systems, right? Now, what we came up with, or before I show that, so one of the main motivations of this problem is that there are these applications. If you are familiar with brain stimulation, there is something that is in use, which is deep brain stimulation. That is the best approach that we have to control neural circuits explicitly. Uh, and there is something that requires you to apply electrical pulses. So if you think about it, there are thousands of neurons, and you insert an electrode and you apply stimulation, not targeting individual neurons, but at a region where the effect of the stimulation is uh, affecting thousands of neurons surrounding that electrode, right? Now, these types of systems are severely underactuated, meaning you cannot individually target signals to neurons. You apply a neuron signal that affects thousands of neurons. Now, and then you cannot also measure what each uh, neuron state is. We don't currently have the infrastructure to measure individual neurons, so we only get population level measurements. All right. Now, it is the same with several of the quantum applications, including pulse design, quantum computing. So if any of you have read anything related to quantum computing, you have in classical computing you have bits, which takes binary values. In quantum computing, bits are replaced by qubits, and these qubits you cannot measure qubits, so you have to sample qubits, and most of the times you have to take statistical samples of qubits, which give you some form of population measurement or some form of probability distribution, right? Now, in many applications, you have this problem where you cannot individually affect or regulate individual agents, and you have to only enforce population level regulation, and you can only measure population level information, right? So an example for these types of system is that you have brain recordings, the EEG that you see, you have hundreds or thousands of neurons. Each of them, they spike at different times, and there is some sort of spike sorting algorithm that is used to say that at T1 there are these many spikes, right? Now, at any given time, you cannot attribute a specific spike to a particular neuron, right? You cannot tell on this snapshot this spike corresponds to this particular neuron. There is no way to attribute that. Now, there are other cases where you can do some form of labeling. So, for example, if you are familiar with monarch, have you heard of these type of butterflies, monarch butterflies? It's one of most uh, uh, okay, one of the very popular studies that have received a lot of funding from federal agencies is the migration pattern of monarch butterfly. So these are very interesting. If you get a chance, you have to look them up. So what usually they do is they tag some of these butterflies to identify or label a particular butterfly and track their population. Right now, we assumed that we can do something like that in certain applications, and we came up with a framework to study such systems, right? And what we proposed, the key results are a bit technical, but I'll briefly mention what it is that we did. So we have multiple systems, each of them obey or they have their own behavior that either come from physics or biology or chemistry. And from those first principle models, we said that there exists a dual model, which is going to give the exact information that you get from the first principles model, but this model no longer depends on whether you measure individual units or not. All you need to do is you have to measure an aggregation of measurements, and you can compute their statistical properties like mean, variance, higher order moments. And if you can track these statistical properties, you can exactly tell what individual agents are doing, right? So we showed that this is possible in theory. And what does that mean in terms of some application domain is, if you have done modeling, most of the modeling is based on some form of uh, established models. And those models in the neural systems, there are many of them. Some of them are listed in this blue box. And uh, each model, they have their own assumptions and limitations, right? Now, if I am doing if I collect data and fit the data to a model, these model, because of their assumptions and limitation, may not capture everything related to that system, right? So the theoretical work that we did enabled us to come up with a different model which captures all the properties of the system without making any assumptions from the data that is available, right? So that is what we refer here as a model, that the data-driven model, which is agnostic to any first principle assumptions that we make. Right? Now, an example here shows that if we have hundreds of oscillators, so I'll start from the beginning. So we have a pattern like this, that is the initial profile of a bunch of robots. And we want these robots to form a final profile that is like this, right? They want to be in specific clusters or clusters of 4, right? And we showed that we can collect data not by measuring individual bots, but taking snapshots of the population and coming up with a signal that can be applied on individual bots. And eventually, we can take them to a particular pattern that we desire, right? So that's what we can do with this type of work. All right, so I'll stop here. If you have any questions, let me know. I think I'm over time by a few minutes, if I'm not wrong.
That's 350.
350. All right, perfect. All right, so we'll stop here. If you have any questions, feel free to ask. Otherwise, you can email me.
So here on campus, what compute resources do you have? Do you have your own host and the like for the AI Institute? Or
Oh, so when I think for the AI Institute, the faculty, some of the faculty members, we contributed some. So we invested in a compute resource that is maintained by our IT department, and it is used by all our students. Okay. Right. Yes.
So a lot of models that you had mentioned in the lecture were actually based on some heuristics or known assumptions, right? Like built upon by some foundational stuff.
Right.
So
But so when you say models, so I had mentioned several models. For example, the models that are mentioned here, none of them are from heuristics. They are all first principle models.
no, I meant the models that we are doing, the approximation.
Yes, the approximate models, and they are not heuristics. They are analytically derived from first principles. But the benefit of models like this is it doesn't depend on whether you can measure each agent in the population, right?
No, but we are still depending on someone building the foundation for the work before we try to build an approximator, right? Or
No, that's what I'm saying. We don't need to depend on that foundation. We can directly go from data to this model. Right? That's the objective also.
So how are the inside, like for example, if we take the neural systems example,
Mhm.
and we're trying to study neurons and how they behave on for a particular stimulus.
Right.
So you are saying like data can be derived as it is without any background information.
Right. So
But getting insights still needs some domain knowledge and some work already being done in it.
getting insight is not the problem that we are addressing here, right? So the problem here is this. So you have data that looks something like this over a period of time, right? So if I have this data, can I inject, for example, stimulus so that I can induce synchronized oscillations or ensure that all the neurons have a specific synchronized state. Do you see what I'm saying? So the goal is mostly on how to collectively regulate the behavior of multiple agents, right? So that's what we can do with this particular approach. We cannot gain a lot of insights with this approach. There is another one which I didn't talk about that is related to perturbation theory that is useful for gaining insights from these types of systems directly from data.
So we just want to look at how the system is working on a global level.
We want to not just see how the system is working on a global level, but we also want to influence the system so that it does something that is desired at a global level. Sure. Any other questions?
Yeah. So there's always an agent.
There is an agent for.
Is there always an agent for each system? Like for this one, what's an agent for this one?
Oh, good question actually. So here the agent is referring to neurons, right? There are thousands of neurons, each have their own behavior that is autonomous, right? So you can influence them independently or collectively. Does that make sense?
Yeah.
All right.
I think Dr. should want to say something.
Well, it's fantastic to see you all guys, see you all asking questions and engage. That's fantastic. Thank you very much, um, Vignesh, for kicking off our seminar. Sorry, I had to be away, and in fact, I'm in car right now. But as usual, so much information and quality information in your talk, Vignesh. And I hope for the students it is clear. Submit no more than 1 page long report on with 2 paragraphs, exactly as I described, by midnight of tomorrow. Always the deadline would be the midnight of the next day of the talk. And submit in a PDF if at all possible. The grading is not at all hard. So you just have to come to the class and submit the report, and that's about it. If there is quality of report is not good, I will give you a feedback. Any other questions? Okay, so I'll see you in the class next Friday.